Hi, Rui. Are you in here?
Hello.
Hi. Thank you very much for coming. Uh, so could you share your screen?
Okay, let me see.
Uh,
Well, I can start from here, I
okay.
guess.
Yeah, I can see your slicer. It's okay. You
Yeah, I think it's fine.
you will share the slide or no? PowerPoint?
I don't have any slides.
Okay, you just use the so only through the slicer or
Slides and maybe um Linux.
uh-huh. But Linux is not on here. Maybe you only so sharing the software. So basically, so the whole monitor so should be uh
Oh,
synchronized better.
let me see. Is that better?
Nothing will change.
Can you see my
Okay, okay. I see. Yeah,
terminal? Okay.
yeah. There's the terminal. And then okay, so you can do the so some of the so tutorial on here.
Yeah.
And soon, please wait. Maybe so 1 minute later, so you can start and so this is recording and so will be uploaded to it YouTube.
Okay.
Okay, this is 1 o'clock and please start.
Hmm. Okay, so today's tutorial is basically just some basic use of 3D slicer and how to view like nifty data and atlas. So for start, I think if you want to view any nifty data, you can just drag it onto the slicer. And the important here is you want to show options, and you want to load as a single file and now as a label map because this is nifty volume. So if you click OK, you- you'll see the data here. So here we have the axial view, the coronal view, and the sagittal view. And you can use the slider to drag to view the volume in different views. And the next, we have the atlas. So same, you want to just drag the file onto the slicer. Make sure here is a show options, and here you want to load as a label file, a label map. Then you'll see like this atlas view. Now this might be a bit strange because we are still missing something. So here, usually for the atlas, they will also provide like a label file. If you want to drag this onto it, and this is basically a text file define the labels. So here, after you load this, you want to go to volumes. You want to select the label. So here's the atlas. So scroll down. So here is a lookup table. So from this table, you want to load the file before. So then you will get the correct color for this atlas. And from here, can go here. You want to first log the views. So anything you change will apply to all three views. So say you only want to see the border of the atlas, you can just press here and you can look through it. And if you
So
hover,
can I ask the basic question? So, you are
sure.
using a color map of the TMBTK ITK lab. So where it's come from here? And what is the data set on you are showing?
Oh, this is the Turone Mouse Brain Atlas. So
Ah,
basically this file is provided by the atlas itself.
uh-huh.
So it's usually it's a text file.
Okay. And
Yeah.
so this where it's come from download. So maybe I download it and but so the Google.
Yeah, I'm not sure where you download it from, but if you search on Google, you should find it. Just search for Turone Mouse Brain Atlas.
Yeah, maybe I can download what this is. Ah, okay.
Yeah,
So,
or maybe you can share the link where.
yeah, I find it. So you just Google TMBTA Atlas, and
Yeah.
you can sort of download on here.
Or
So
if you unzip it, you should get all of this.
yeah,
So
I
you have
remember.
the template. It's the NIfTI file under the atlas. Then you have the atlas file, which should have the atlas itself and the label.
Hmm. I understand. And this is a so T1 だったか T2 weighted image.
I think it's T2.
T2? Uh-huh, weighted image.
I think maybe it's here. Uh, yes, T2.
Hmm. So this is so averaging the
Yeah.
high resolution, so 60 micrometers, so it's perfect
So
data.
so when you go to volume here, you can see the image spacing. This
Uh-huh.
is basically the size. So 60 micron
Mm-hmm.
resolution.
Okay, I understand.
Uh, yeah. And if you hover over each atlas region on the bottom left, you should see the area name. So here's layer 5, layer 6A, layer 5, layer 2, 3, etc.
Okay.
So here's what you should see, basically.
Mm.
So now, if we close this, and let's load one of Yagishita-san's data. Well, let's see, we load this. Make sure we're now loading as a label. So you can see there's few problems here. Firstly, the brain is
Maybe I think
inverted.
so. We are so starting on the discussion about the what is the data also. Yeah, maybe so. There's not only the so Yagishita-san's laboratory, so there's another so people on here.
Yeah,
So that means that
but
so
we use this as an example.
yeah. So this
Yeah,
is so MRI data from the Yagishita laboratory in Tokyo University, and this is a
yeah,
mouse data and so T2 weighted. image data and with so some kind of sculpt, I don't know. But
Yeah,
so
just include the skull of the
uh,
mouse.
and the your purpose is that so registered from the individual brain to the so this template data set finally.
So if we compare to the atlas we see before, you can see the brain is inverted and they are in the wrong view. So this corner view, it should be here. So here's the corner view. And in order to do the registration, we need to fix this first. Fix so it's in the correct view because ant is not smart enough to know this brain is inverted. So to do that, we go here. So we're going to go to transforms. First, we want to create a new transform. Make sure we are applying to this brain we just loaded. So in order to rotate this brain to the correct orientation as the atlas, so from left and right, we want to do 90 degrees. They want to do 180 here and 180 here. So now this is should be very similar to what you see before. Same orientation as the atlas. So we need to register this brain to the atlas from this orientation.
Sorry,
So
may I ask
here,
you a basic question? Like how we can confirm where is the left and where is the right side?
uh, I guess if you go back to here, I think you just compare whether it's the same image but like rotated. So
Ah,
here the left side of the brain is here, right? And the
okay.
right side here.
Okay.
No, I think if the right square, I don't know, a kind of box in the right
Oh, sorry. So this should be the left.
left, right? Yeah. So
Yeah.
just to make sure whether this 3D slicer properly reads the transform matrix of the NIfTI file. So probably yes, because it displays some information on the left side.
Yeah, yeah,
I just want to make sure.
sure. So first we need to rotate this, right? So
Okay.
uh,
So this is
yeah.
basically manipulating meta information about NIfTI, right?
We are applying a transforming matrix.
Transform matrix.
Yeah.
And so my question is, so whether this 3D slicer is compatible with meta information of NIfTI file. The NIfTI file also contains, these orientation information and whether it properly reads. Otherwise, if the 3D slicer just treats the boxes, images, just as a series of intensity information, it may disrupt the original information about the orientation.
I mean the original orientation should be what we see before. That's just the raw data.
Not just the raw data, but if the NIfTI file also contains rotation information.
Yeah, then I'm not sure, but
Not
if
sure.
you're
Okay,
using slide,
we need to check. Okay, thank you.
Yeah,
yeah,
so basically, so let me so confirm the basic situation. So this is a NIfTI file. So that means that so there's a information to coordinate. So MRI coordinate or something. And if you go to the
so if you go to volume here, all the
uh,
information should be here,
this
like
is
the origin, spacing.
So if we save this file, let's say as the new NIfTI file, so this new coordinates, the rotation coordinates will be saved as well with the image.
Yeah, it will be like what we see here.
Okay.
Then we can just apply the inverse to go back to the original. so there's no problem.
Okay.
Yeah. So here after the transform, you want to apply. So harden transform. So then we can save this. So let's save it here. It's the same name as the original. So now we can check whether it's saved properly. So we'll open this. So it should be in the correct orientation now. So to do registration, we need to start from here, basically. So to do the registration, basically it's quite easy. I think the hardest part is actually install Ant and to get it to run. That might be the hardest part. So I'm using Windows. So for Ant, I'm using the Linux subsystem. So I install Ant here. So there's no problem. You should be able to use. So basically you can check whether it's installed correctly. So Ant registration. So this is the script we want to run. You can see with the so everything is okay.
And maybe so we should also check that Ant software itself. And you will so firstly download the Ant softwares.
So if you go to the Brain Minds data portal
Mm-hmm.
and you go here, go tutorials, and you go here. So I wrote a tutorial on image registration.
Mm-hmm.
So if you click here, there's like instructions you need to follow to install Ant here.
Mm-hmm.
So you can go to the GitHub.
Mm-hmm.
Basically, what I did is compile from source. So
Mm-hmm.
build from source. This
Also,
will always give you the latest version.
mm-hmm.
Because if you're using download binary or conda, something like that might be like older version.
Mm-hmm.
So you can then see the current version is from July 24th.
Mm-hmm.
So it's quite new. So the tutorial is already outdated, you can see.
But
But
anyway,
it doesn't matter.
so we can download and so just work on the Mac or Linux and Windows on the Ant softwares.
You
And,
just follow the instruction here. I had no problem doing that.
and
So build from source.
here you will use so these are the paths or is also necessary. So this tutorial is on here.
Yeah, just follow the instruction here. You should be okay.
Mm-hmm. I understand.
Either you're using Windows or Linux. I mean, I did it on Windows, so
Mm-hmm.
should have no problem on Linux. So just
Ah,
follow all of this.
the other
Yeah.
way so just a binary so data is downloaded or so condas and automatically so installs is also existing.
Conda version is the Python one.
Ah, okay.
If you want to use the like the programming one, you need to do
Mm-hmm.
this.
So that means
So
that so
conda is and for Python. That's different.
okay, I understand. But anyway,
Yeah.
so we can use this way. So there's a tutorials on here.
Yeah. Please follow this. Yeah. To install ants. That might be the hardest part, but just something you need to do.
But my
Um.
experience, the binary download is always work well. So if the
Yeah.
Mac
Yeah.
this
But
is
I had people that had problem doing that. So
yeah
yeah,
yeah.
depends on. Yeah. So once you install that, and you can try to run this script. So and registration ISYN quick dot sh. So it's a shell script. So to do the registration, we just run this, just a bunch of commands. So first thing is the dimension, since we're working with volume, so it's 3D, so 3. So next we want to set the fixed image. So that's the volume we want to register. So I think that's, let me see, the Turone will be the Mouse Brain Template. So it's this file, tmbta. tmbta brain templates. NIfTI. So the next is moving file. So that's the file we are registering. So that will be the file that we rotated and saved. So it's the T2 when I turn down NIfTI. So then I want to set the output. So say just out. And we can see set the number of cores we want to use. So that's depend on your CPU. So for me, I usually use 16. So then we'll run the registration. This should complete quite fast. So it's about 11 seconds to register using the script. Now let's just wait till everything's saved. So now we'll have some output. So we'll have the generic affine. So that's the affine transform. Then we have two warp file. So that's warp one. So that's warping from this file to the template. And the inverse warp. So that's warping from the template to back to this file. And here we also have two warped file. So this one will be this file warped to the template. So we can take a look. Now if you load this, this should be this file warped to the Turone template. So if we also load this, now we want to lock the views. So here, if we select the warped here, then we can change the views. We can see how well the brain register. You can see it's mostly okay. The registration. And now if we load the other one, or the inverse warped, this should be the Turone template warped to the this file. So if you overlay them, you can see they're in the same space. Now, how can we use the transform files? Say we want to mapped the atlas from the Turone template space back to the individual space. So this one. So here we'll do ant apply transforms. We can check all the input you need to have. So first the dimension, it'll be 3D. The reference value will be the individual. So it'll be T2, 7. And the transform we want to apply it to. So the input that will be the Turone atlas. Brain atlas. So brain atlas. So the output, let's see. So output, let's see. Turone to individual. 1 and 7. So here is quite important. We want to so the N is for interpolation. The default is linear. And since we are transforming a label file, we cannot use linear interpolation. We want to keep the original labels. So to do that, we can use nearest neighbor. And around this. Okay, let me see. I think something's wrong. And supply transforms. Don't know why. Maybe this is too long. Or I spelled it wrong. Yeah, capital N. Okay, let me see what's wrong. So we'll have the dimension, input, reference value, output, interpolation. Oh, sorry, I forgot. So the transform we want to apply. So since we're using the inverse transform, we need to apply the inverse of the affine first. So to apply the inverse, we need to put a bracket on it. Put one here, so it's the inverse. And then we want to apply the inverse warp. So that'll be this one. Now it should run. Okay. Let's see what's wrong here. Okay. Why? Let me see. I'm not sure why this is not working.
I don't recall.
Everything is correct.
So
Sorry, let
just
me.
so what we can specify two parameter t.
なんか、ヤギちゃん is talking something.
Yeah. So I just wondered why you need two parameters for t transform. I couldn't understand that point.
So the transform is applied from the right side to the left. So to apply the forward transform, we need to apply the affine first, then the warp.
Oh, okay. So you can apply multiple transformers, right?
Yeah, so
Transform.
we
Okay.
are so here we're applying the inverse warp first, then the inverse affine.
Oh,
So basically, the ANT software are making the two files. The first is the affine transformation, and the next is the deformation pair. So this is the NIfTI file. So this mat file NIfTI file is some kind of pairs of the so one ANT resolution cases. And the ANT apply transform, so the apply the NIfTI file, the warping to the other other rotation or something. And the first is so the right is the first transformation, and the next is the next transformation. In this case, is first is the inverse warp. So the inverse warp deformation is going to firstly apply, and next inverse warp. So there is a なんていうか、カッコ and so slash one means so inverse affine
Yeah, the
operation
inverse of the affine.
is so minus t out genetic affine dot mat one. So if you removing the one cases, so this is a so usual, so just a normal affine is applied.
Yeah, sorry, I know what's wrong. I got mixed up with the registration. So the output need to be the full file name, not just
Mm.
the front. So here should work. So now, okay, let's close this. So if we load the individual, then we load this. This should be the atlas, Turone atlas that's applied to the individual space. So when you load a label, make sure here is check. It's a label file. So same as before, we will need the label region definition. To do that, we go to volumes, and select the label, and the lookup table will be this one. So here we have the Turone Mouse Atlas mapped to the individual space. So if you want to go back to the original position, we can just apply the inverse. Well, let's apply to both of those. So that'll be minus 180, minus 180, then minus 90 degrees. So here we went back to where we started in the original position with the atlas map to it. Okay, is there any questions?
So here you use affine transformation, but does ANTS provide more sophisticated registration algorithms so that we can, I don't know how to say, but nonlinearly or locally optimized masking?
Yeah, so here we also have the warp field. So it's not just affine transform. We
Okay.
have warp. So you can actually see this in the slicer. So this is a warp file. So you can see how each pixel is warped in which direction during the registration. I mean, each color represents a direction. So
Okay, good. So
it's not just a linear.
Okay. So what you have shown is after using this nonlinear transformation, right? But I see
This and the affine. So
inverse one.
both. Yeah,
Both.
both.
Then can you try to apply not affine but more both? Okay, both.
Yeah. So here we are applying like the inverse. So if you want to apply anything from the individual to the, say, the Turone space, you will do the same thing. But you want to have the reference volume as the Turone. The template. So the input can be, say, if you made a mask in the individual space. So just for example, say we have a mask for this brain in the individual space. Or we can say in the Turone. So here we need to apply the warp first. And then the affine. Remember this is applied from right to left. So the affine is applied first. Here, we don't need to inverse this. And make sure you're using nearest neighbor. If you are transforming a label, if you're transforming a volume, you don't need to use the nearest neighbor. Linear is fine.
Okay, thank you. So my point is, can you display the overlay again about after you applying Tornado atlas towards our individual plane?
Okay. You want to see the atlas?
Yeah. So again, every time. So the dorsal part is fine, but in the ventral part, if you take a look at the, left bottom of the image, so on the left bottom column, on the left bottom of the, oh, yeah, that part on the left.
Corner wheel.
So yeah, and you see, some boundaries, you know, exceeded from the boundary of the brain.
Yeah, the problem here, we are registering a brain with skull to the templates that's without the skull. So to do a better registration here, we can use the image that got skull removed. This should give a better registration. So actually, we should register this to Turone if we want to have a more accurate registration. So we need to remove the skull. But if we're registering the brain with skull, so you should register to the average brain that I made that has the skull.
Mm.
Here we're simply using a Turone as an example. But if you want to register Turone, you need to use a brain without a skull.
Mm.
I'm just wondering if there is any additional parameters during the quick registration that can be specified that can improve the registration of the
Okay,
individual.
if we scroll up, you can see actually the full AND command. Square all the way up. Keep going. So this here is the full command. So you can see there's a lot of parameters you can change here. But what each parameter means, you need to look them up because it's quite complicated.
I see what you mean, but in that case, those are default parameters that were specified during the quick registration.
Yeah.
Okay, this makes sense. Okay.
So you could copy this and change some parameter and run.
And then just iterate through couple. Yeah, makes sense.
Yeah.
Okay.
So I use the quick as a example because it's quite fast. So there's also just cyan without a quick. So this is much slower than quick. So it's not good for this tutorial because this will take too long. So this will basically warp the brain much more compared to quick. In some case, it's better, but in some cases not. So you need to test. But I mean, if you want to provide as like online system, this might not be the best one to use because we take way too long.
Makes sense. Thank you.
Yeah. Any other questions for
Is there is any
comments.
automatic way to rotate all the samples at the same time, just running one command instead of manually changing their rotation every single time?
So um here the transform, you remember that we made. I think it's let's say we apply to this. So that's 90, 180, and 180. So you can actually save this transform, H5 transform, and you can apply this transform using and apply transform. So basically you want to apply that first. So what you need to do is that transform dot H5. You can do this as well.
But it will only apply to the individual brain, not for all the other subjects that we need to analyze.
Individual. You just make a script to do all the brains.
Okay.
Yeah. But if you want to do this, you need to make sure that the
Should we
reference
also,
volume here
yeah,
should be the one that's already rotated.
okay.
Because if you use the original reference volume
Mm-hmm.
and you apply this transform, it will keep the same like 3D space. So let's say the corner view will be cut off.
Okay.
Will be
So if
cut off like
so what I
this
understand
like this way.
is
Yeah.
it's better to take the individual brain, register it to the reference image and to the label image. That's how we ensure that we have that .mat file inverse, right? And then to apply all the relevant transformation to other individual brain, because only the .mat file is available to us when we are perform the registration on one brain only. That's
If
where
you
we
do
get lost.
one brain, you should get a mat and a warp.
Mm-hmm.
You should get those 3 files at
Yeah,
least.
yeah.
Yeah.
But so the procedure is I take one brain, I rotate, and then I register them to the reference image, to the label file. Then
So you take that brain, you rotate to like this
Mhm,
in the correct orientation, then you register.
mhm. And what about others? So I just can apply that H5 transform file to others. So, and they will be the same.
Yes, as long as they are consistent with the one you are applying to. So they are all like upside down.
Mm.
So you press like another one. Yeah, as long as they are like this, you should be okay.
Mm. Mhm. Thank you.
So if you want to register from here, you need to apply the H5 first, then do the transform.
Okay.
And you can apply the inverse of the H5 last if you want to go back here.
Yeah, that makes sense.
Yeah.
By the way, do you know, I'm sorry, this might be too specific, but do you know why this plane looks upside down? Because we properly set the parameter.
I
Yeah,
have no idea.
this is where every single image comes from the Bruker machine. Our images look like this all the time.
Okay,
All the
then
time.
this is correct. So then
Yeah.
we should not, you know, even if you may think this, you correct something, but this should be wrong because we set coordinates parameter properly.
Yes.
So this is, so what you have to do is just rotate from mouse atlas to human atlas, but
Mhm.
other things should keep in the original way. So, or I don't know. I need to understand why sometimes this appears in like this.
Yeah,
Yeah.
the thing about the orientation, I mean, we have the script that automatically rotates to the template that we need, but I mean, it's kind of weird, and I believe that that's all subjects that the Abesan provided to us, and they were like that. It's from before we actually change something to the orientation in the broker, as
Oh,
far
I
as
see. Okay. So because these data are old, they are
yes,
fixed, and the
yeah.
latest one should appear in a proper way.
Not to the human coordinates. We still need to rotate, but
Yeah,
that
yeah.
rotation
One
it's
direction, I
different.
know.
Yeah,
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 I see.
And one last thing, if there's anything you didn't understand, you can just refer to this tutorial here. It's quite detailed. There's like data you can download to just do exactly this. This is for the marmoset brain and atlas. So there's detailed commands on what each parameter means, and you can download the data and try. Yeah. So any problem or question, you can refer to this.
makes sense. No, for now, I believe yeah, it's okay. Thank you.
Okay. Any other questions?
Okay, then I have a question. So, here you said that you only use a simple parameter for registration to save some time. But so, could you tell me some tips about how to explore parameters for registration to obtain better result?
Um, I mean, usually, and registration quick is sufficient most of the time. Because if you use the other script, the one without quick, sometimes it like over warped the image, so deform the image on areas you're not expecting, and it takes much longer. And also in the script itself, there's like some parameter you can fine tune yourself. Say have a look at the script. Um, so you can change the transform type. By default, we are using the I think it's S, so rigid plus affine plus deform by SYN. I mean, you can try some others, be spline, things like that. Also, for the command here, you can also say provide some landmarks or mask. So if you want to do that, you want to add some additional. So you want to add another fixed, say we have mask or um, Turone. Say we have a mask. Then we also have a mask. Sorry, not mark mask. Um, mask for. So we can add some additional constraints, say mask for the brain. So then we're matching both the volume and the mask at the same time. And this will make the registration much more accurate because we know exactly they should match in the mask space. That usually gives you a much better registration.
Okay, thanks.
Yeah,
And
so
one more,
additional constraint like mask.
yeah. Great. And one more question is, so can you calculate the, like regional brain volume using warp file? I
Regional
mean,
brain
brain
volume.
volume difference. So using like free surfer or the program, we typically want to know the brain volume difference, but probably the warp file reflects the volume difference, right?
Warp file is just where the pixel should move in which direction. I think that's different than the volume. I mean, if you have a mask for the brain, I guess you can calculate the volume of the mask in pixels, then compare that, maybe. Sorry, I'm not very familiar with that.
Yeah. Okay. So probably if we take a look at the atlas, yeah, I see. Yeah, we can calculate the volume for each region. Okay,
Yeah.
I see.
Say if you map the atlas to the individual, for the same like brain region, you can calculate the number of pixels in that region, then compare. Because you know the size of each pixel. So individual space 100 microns. Yeah. Okay, any other questions? Okay, if there's no other questions, then we can conclude this tutorial. Okay, Nakai-san.
Okay, thank you very much for the so great tutorials. And if there's any question and comments, so please send email to the Rui or me, so it's possible. And this tutorial is uploaded on YouTube. So if there's something problem, please tell me. And Rui, and thank you very much for the today's tutorials.
Okay, thank you.
Okay, that's all.
Thank you very much. Yeah.
Thank you
Yeah.
very much. Thank you.
Maybe so we will do the so another so tutorials or the so Optinis or calcium imaging so software developed by the Doer in OIST will be maybe next month. I forget the detail, but anyways, I also sending through the other opportunities. Thank you very much. See you.
Thank you.
Thank you.
Bye.